Welcome back, guys. So we are continuing with the 2023 prelim for chemistry 2023 of Gauteng. That was written on the 26th of September. So yeah, we're resuming with the paper here, and now we are doing question 6, right? So question 6 is about chemical equilibrium, right? So chemical equilibrium, there are factors that affect it, and right, yeah. So that's what it's all about in an essence. So when the rate of the forward is equal to the rate of the reverse, okay? So it says here, hydrogen gas is prepared by the reaction of methane. Methane is C4H. CH4. It's a organic compound, okay? And then, and steam, right? So that by steam, they mean water, but not just water, the gas of water, the gas form of water. So it says that as shown in the following balanced chemical equation, right? And then it says methane and steam are sealed in a 2 decimeter cubic container to react and are allowed to reach equilibrium at temperature T. So we don't know that temperature, and I don't think we need to, but let's resume and see what they want. So these people want us to state Le Chatelier's principle. So Le Chatelier is a simple guy, okay? So this guy, he comes, and says to us, equilibrium has now been disturbed. So he wants to put it back. So that's what he does. So he has one mission. It's just to reinstate the level of equilibrium once it's been disturbed. So obviously the system should have been in equilibrium in the beginning, right? And now that the system's equilibrium has been disturbed, okay, this guy now wants to reinstate it by favoring the reaction that opposes the disturbance. So I love the guy. The guy lives in Cape Town, right? Le Chatelier lives in Cape Town. He's a Capetonian. And the reason I say Cape Town is because CPT, right? And the only things that can affect the state of equilibrium is what? Concentration, the pressure, and of course the temperature. Okay, so those are the things that we should be looking out for. But other than that, let's resume. So now, after stating Le Chatelier's principle, let's go to 6.2, right? So 6.2 tells us that we should use Le Chatelier's principle to explain how the following will affect the yield of H2. So let's understand something. Yield means basically what concentration of something is produced, or number of moles of something that is produced. Okay, so now we are focusing on this H2 guy, right? But before even that, they've given us a piece of information that is critical that may help us in answering this question. They tell us that delta H is 206, right? So the 206 doesn't really matter. The number doesn't really matter. But what we have to understand is that delta H is greater than 0, which means it's positive. So what this means to us is that this is an endothermic reaction. And how we can must show this on this reversible reaction that we have is that the forward reaction is what? Endo, because that's an endothermic, okay? And then the reverse reaction is exothermic, okay? So that's something that we can note. So this value of delta always tells us about the forward reaction. So now, understanding that, it says we should use LCP to explain how the following will change, following changes will affect, right? So now what they tell us is that they are adding more CH4, okay? So CH4 is a reactant, okay? So now they increase that guy. So what this basically means is that they increased the concentration of CH4, okay? And remember, Le Chatelier comes in at this point where we've increased the concentration, which is one of the factors that affect the state of equilibrium. But Le Chatelier wants to reinstate that equilibrium, right? So the only way he can reinstate it is by favoring the side that opposes the disturbance. So the disturbance is this increase in temperature. So now it means that Le Chatelier will try to decrease this guy because he's the one that's moshing the equilibrium. Okay, so what this means to us is that this guy needs to react to form the product, since he's a reactant. So what this means is that you can even add that according to LCP, right? What we want to do actually is we want to decrease the concentration of this guy so that we can oppose this disturbance. And how we decrease this guy is by producing more products, because he is a reactant, he or she. Hey, let's be safe for one. But this is the second point. So the first point, you can just say increased concentration, and you say according to LCP, this guy will try to decrease the concentration of that guy, right? So if we're trying to decrease the concentration of that guy, this means to us that the forward reaction is favored. So now this is the points that we have, right? These are the facts that are happening here. But the question actually was, how will this affect the yield of H2? So remember, H2 is a product. So if more products are being formed, aka the forward reaction is favored, this means to us that the concentration of H2 gas, right, will increase. So that's what will happen to this guy here. So you could even write that the yield, since they put it in that way, the yield of hydrogen gas increases. Okay, so now we're done with that question. Let's move on. It says 6.2.2 says a decrease in the volume of the container. So remember that volume is not one of the factors that affect equilibrium, but understand something. Volume, right? So let's do this. Volume, right? Volume is inversely proportional to the pressure. I could say that. Okay, so yeah, there's a formula here and there, but now let's just focus on the question. Okay, so it means that if we increase the volume, the pressure will decrease, and if we decrease the volume, the pressure will increase. So what this tells us now, that since volume is not part of the factors that affect equilibrium, but it is directly linked to that factor that does. Okay, what this means to us is that, in an essence, what the examiner is telling us here is that, let's choose this color. What the examiner is telling us is that there is an increase in pressure. So that is the disturbance that is caused. Okay, so now how will we try and bring back the equilibrium according to LCP? Because that's his mission. Okay, so now let's understand something. LCP, right, according to Le Chatelier's principle, they say that an increase in pressure, right, will favor the reaction with a fewer number of moles. Reaction with fewer number of moles, right? And the number of moles does not necessarily mean we have to calculate the number of moles using N is equals to M over M or CV. Not like that. What we mean by that, we're talking about the balancing coefficients of these guys. So now we can see that we have 1 mole of CH4 and 1 mole of water, right, or gas, or H2O. So in total, the reactants, we have 2 moles of that. And then here we see that we have what? We have CO, 1 mole of that, and 3 moles of hydrogen. So in total, on the product side, we have 4. And remember that according to Le Chatelier, an increase in pressure will favor the reaction with the fewer number of moles. So which reaction will be favored? It's the reverse reaction, because that is the one with the fewer number of moles. So these guys will be favored. So more of them will be produced. Okay. So what this means to us, that what? The reverse reaction is favored. So now when the reverse reaction is favored, what does that mean to the yield of H2, since that's the question. So if we are producing more reactants, it means this guy is also going to be used up, because he is a product. And if we're creating reactants, remember this is a reversible reaction. The products can also create reactants, okay? So now if we're creating reactants, it means what? The concentration of hydrogen gas will decrease. So you could also say that the yield of H2 decreases. And then yeah, let's move on. So we've answered that question. Okay, so now they say that the sketch graph below shows the changes in the number of moles of methane, steam, carbon monoxide, and as the reaction proceeds, of H2 gas in a 2 deciliter cubic container, right? So what is important, right, that they've told us is that this is a sealed container. Okay, so in a sealed container, we understand that there is a closed system. And remember that equilibrium needs to be in a closed system in order for it to occur, in order for us to reach chemical equilibrium, right? So in this case, what we have here is a graph. So this tells us the changes in the number of moles. So what this tells us, okay, is that with CH4, we started with 1,4, and then it was used up until a particular point. We don't know how far. And then with H2O, it started at 1,2, so that's the initial number of moles. And then what we can see here, right, which is evident and which makes sense, is that the number of moles of the products, which was carbon dioxide and carbon monoxide and H2, okay, were at 0. Obviously, the products had not yet been formed, but now they rose up, okay, and they rise up according to a particular ratio. And if you look back to the ratio, right, we had 1 mole of this guy and 3 moles of this guy that was there in the equation. So it makes sense why this guy is rising higher than the other. But in this case, so this is the graph that tells us. And then now we can see, no man, at T1, these graphs go flat. Yeah, no. So what this tells us is that there is a constant number of moles. It does not necessarily mean that the reaction is complete, because if the reaction is complete, we're supposed to see that the limiting reagent is being used up. And as we can see, that these 1,4, right, and this 1,2, which were the reactants, none of them went down until 0, which means that none of the limiting reactants have been used up. So the reaction is not yet complete. But what we see is that we see straight lines there. So this tells us that this thing has reached a state of chemical equilibrium. Okay, let's move on to the question. So it says that write down the reason why there is no change in the number of moles of each of the gases between times T1 and T2, right? So we've just explained that right now. So 6.3, right? The system has reached chemical equilibrium. Okay, so that's what's up, and then that was 1 mark. And then now for 7 marks, it says that use the information on the graph to calculate the equilibrium constant Kc, okay, for this reaction at temperature T. So one of the methods that we can use, or we usually use, is the Rice method, right? So let me just pause the video and draw the table, okay, and then I'll see you in just a second. Okay, now that we've got our table, let's resume. So now we have something that they give us here, okay? They give us the initial number of moles of everything, right? So we're going to be filling in that. So now we're going to be using our Rice table, but before we move on to the initial, let's start with the ratios, okay? So in the balanced reaction here, let me just clean this up. In the balanced reaction here, we can see that we have 1 mole of CH4, 1 mole of water, gas, and then we have 1 mole of carbon monoxide, and then we have 3 moles, okay, of H2, right? That's the balancing ratio, okay? So now for initial, they've given us this table for a reason. This graph for a reason. So we can see that before these reactants are used up, are going down in the number of moles, they have somewhere where they start. So now let's understand something. They start at 1,4 and 1,2 respectively, okay? And they form products. And these products, as we can see, they start from 0, because in the beginning of the reaction, you only have reactants that form products later on. So the products can only emerge once the reactants are being used up. So in this case, we can see that for CH4, we started off with 1,4, right? So this is 1,4 moles. This is all in moles, guys. And for hydrogen, for H2O, we started with 1,2. And obviously, for these two guys, we started with 0 and 0. Okay? So now that we filled in what we had initially, let's understand something. We can all agree that the reactants are going to be used up and the products are going to form. So these number of moles that are here are going to go down. So when you come to the C table, let's just put a minus here, because these are going to be reduced or going to be used up. But the products are going to, right, have a positive change. They're going to gain something. So now that we have that out of the way, let's understand something. They've given us something very, very important. They've given us the change. The number of moles of carbon monoxide at equilibrium which is 0.6. And how do we know it is what? It was at equilibrium, because we can see that the number of moles was constant at that stage. So we can all agree that 0.6 was the number of moles of carbon monoxide at equilibrium. Okay, so now that they've given it to us like that, let's fill this in. So now we say that at equilibrium, right? So we're going to go to this column here. At equilibrium, we had 0.6 moles of carbon monoxide. So now that gives us an opportunity to fill in a lot of things in the graph. So let's resume. So now what we're going to be having here is that we had 0. So we added something and then we got 0.6. That's definitely 0.6. Okay. And then let me just change the color just to show the difference. Let's use orange. Okay. So now that we have that, this change and the ratio go hand in hand. So what that means for us is that we can use that change in conjunction with the ratios to identify the changes in the other substances. So what I mean by that is that carbon dioxide and H2O is 1:1. So this obviously going to be 0.6 here. And then 0.6, 1:1 with CH4 as well. So this is also going to be 0.6. Okay. But with H2, it's 1:3. So it means that we're going to have to take this 0.6 and multiply it by 3. Okay, because of the ratio. So the change in this one is going to be 3 times the change of the other. What that means, this is going to be 1.8, I believe. Okay, so that we have 1.8 there. But now that opens doors for a lot of things. Now that we have initial and the change, we can find out what we had at equilibrium. So we had 1.4 initially. What was used up was 0.6. So definitely this is 0.8. And then we had 1.2 here and 0.6 was used up. Definitely this is 0.6 here. And then obviously here we had nothing. And then 1.8 was the change, okay? Was what was gained. So obviously we're going to have what? 1.8 here. So we have the number of moles at equilibrium. But remember, we need the concentration at equilibrium in order for us to what? To calculate the Kc value that they're looking for. So what we should understand at this moment is that we have a volume of 2, and we know that concentration is the number of moles over the volume. Okay, so obviously here we're going to have what? 0.8 over 2. That is our concentration, and definitely we'll get 0.4 here. Okay, and then here we're going to have 0.6 over 2, which is definitely 0.3, and then here we're going to have 0.6 over 2, which is indeed 0.3. Okay, and then here we have 1.8 divided by 2. This is what? 0.9. So we have the concentrations at equilibrium. And then now that we have the table filled in, then we can definitely find what they're looking for, which is the Kc value. Okay, so remember that Kc, right? Kc undercover. Kc is equals to the what? The concentration of the products, right, over the concentration. Remember, the square brackets represent concentration of the reactants. Okay, so by virtue of that, remember that this is not like necessarily a formula. Okay, you just need to apply it. You don't need to write this in the examination or on your question paper, on your answer paper, right? So now let's just fill that in. So the products that we have, okay, we have the products as H2 and CO3. And then now remember that when we are doing Kc, your ratio becomes your exponent. Okay, you'll see that now. So now we have concentration of H2, but because its ratio is 3, then this is obviously going to be to the power of 3. Okay, let's move on. And then multiplied by the concentration of carbon monoxide, which was also formed, but that's only to the power of 1, which doesn't make any difference, all over. Now we're moving to the products. Okay, the concentration, let me just start with CH4, right, and its ratio was 1, so it's to the power of 1, multiplied by the concentration of OA, okay, H2O, which was 1. And something to note, right, in this case, all of these guys were gases, okay, But remember, in KC, right, we only regard the gases in the aqueous solutions. So if you have a liquid or a gas, its concentration here is going to be 1, okay? So that's just something to keep in mind. And then definitely here we have of hydrogen. So hydrogen, we just got it. We said it's what? 0.9. So we're going to have 0.9 to the power of 3 multiplied by the concentration of carbon monoxide, which we got as 0.3 as well. 0.3 all to the power of 1 doesn't make any difference. And then here we have 0, for CH4. We have what? We have 0.4 for CH4 to the power of 1 doesn't make a difference. And this is to the multiplied by 0.3, which is the concentration of water or H2O gas, which is also 0.3 there. So now we just punch this on our calculator and then we will get our answer of KC. So I'll just do it in a second and then, yeah, let me get my calculator. And then what I get on my calculator is 2.03 rounded off to 2 decimal places, okay? And remember that KC does not have a unit because KC is simply the ratio of the concentration, right? So ratio does not have a digit, okay? So yeah, ratio doesn't have, a unit, I meant to say. So let's move on. The last question asks us, it says, the temperature T is decreased. How will this affect the KC value for the same reaction above? Okay, let's just look at this in more detail. Okay, so it says the temperature is decreased. How will this affect the KC value for the reaction above? Right, down, only increase, decrease, or remain the same. So there are a lot of ways people can do this. Some people say that a decrease in temperature, the way it is, right, the decrease in temperature decreases the KC value. But let's see how it does that, okay, to have a bit of context and, understanding into how it works deeper. So now we're talking about temperature, and remember that we identified, okay, that this side is our endo. How do we know that that side is our endo? Is because our delta H was positive 206. So now, as long as delta H is positive, our forward is endo, and our reverse is going to be exo. Right? So let's understand something. They said they have decreased the temperature. So according to LCP, who's this Le Chatelier, friend of mine, he says that when we decrease the temperature, we favor the exo. So T down, we favor the exo, and obviously vice versa works. If we increase the temperature, we favor the endothermic reaction. So now we decrease the temperature, it means that we favor the exothermic, and we've just identified that our exothermic is what? Is the reverse reaction. So what this tells us is that more reactants will be formed because we are favoring it. You get? So now look at this. Kc is equals to what? Concentration of, I'll just say PR for products over the concentration of the reactants. And now what's happening here, right? I just like doing these things in mathematical way. It makes us understand, right? So now it says that Kc, okay, is the product over reactants, okay? So now if more products are being formed because the exo was favored, if more reactants are being formed, if more reactants are being formed, it means that this guy's concentration will go up. And just understand something. I have a number and I increase the denominator. It means I'm decreasing this guy here because right? Does it make sense? Okay. Yeah, it means I'm decreasing that guy there. So yeah, so I have 2 over 4. Okay. This is 0.5. But now I'm increasing the denominator. So it's still 2 there, but it's over 5 now, for example. This is 0.4. Okay, so we can see that when we decrease the denominator, our expression decreases. Okay, so we could just say Kc for 6.5, the Kc will decrease. Okay, and then yeah, so we are done with the chemical equilibrium of this question paper. This was 17 marks in the Gauteng Prelim of 2023 of the paper 2 chemistry in Gauteng. Right, so yeah, thank you for watching, and yes, you can just share with your friends, and yeah, just share your opinions, and then yeah, let's talk in the comment section, and how did you think of this question? And yeah, have a good day. Sure.